All right, today we are diving into something truly game-changing in the world of AI. It's a technique that is completely rewriting the rules on cost and accessibility. And you know what? It's a story about working smarter, not bigger. And it all boils down to a fascinating and surprisingly simple question of geometry. You've probably felt this, right? The most powerful AI, the kind that really understands language, it always seems to be locked away in the cloud, run by these massive tech companies. It feels like you need a billion-dollar data center just to play the game. But why? What's really going on here? Here's the number, 3 terabytes. That's how much RAM you need to make just 1 billion pieces of text searchable by an AI. And listen, that's not storage we're talking about. That is active, super expensive memory. A number like that just immediately prices out almost everyone. Startups, researchers, you name it. For years, the answer to every AI problem has been more compute, bigger models, just throw more power at it. But what if that's just the wrong way to think about it? What if we've been using brute force to smash a square peg into a round hole when the real issue is something way more fundamental, something about its shape? Okay, so let's really break down this billion-dollar problem. The heart of modern AI is this process of turning language, words, sentences, whole books, into these long lists of numbers. We call them vectors. And these vectors, they're meant to capture the meaning, the actual vibe of the text. And we're not talking about a short list of numbers. A standard high-quality vector has 768 of them. 768 dimensions for a single thought. Now, imagine multiplying that by the billions of articles or products you want to search through. The cost it explodes. And that's the barrier to entry right there. Now here it is. This is the big aha moment. The problem isn't that language is so complicated it needs 768 numbers. No. The problem is that we've been trying to stuff our data into the wrong-shaped mathematical box. We have a fundamental mismatch of shapes. Think of it like a library, okay? The way we've been doing things using what's called Euclidean space is like taking every single book you own and just throwing them all onto one giant flat floor. It's a mess, but language isn't flat. Just like a real library, it has a structure. It's a tree with these beautiful branches going from science down to physics and then branching again into quantum mechanics. And this table right here shows you just how quickly that becomes a disaster. A tree structure that's only 20 levels deep has over 1 million different nodes. 1 million. If you try to flatten that out onto a simple linear floor plan without everything piling on top of itself, well, it's basically impossible. You'd need a ridiculously huge number of dimensions just to keep things separate. So if our flat floor is the problem, what's the solution? Well, it's pretty intuitive, right? We need a space that is shaped like our data. We need a space that already has a tree-like structure baked into its very fabric. We need a space that actually bends. And believe it or not, that space has a name. It's called hyperbolic space. It's this wild, mind-bending kind of geometry that people started exploring way back in the 19th century. And it turns out, its core property, that it grows exponentially, is a perfect one-to-one match for the structure of language. Now, a great way to actually picture this is something called the Poincaré disk model. It's a clever map that fits this infinite expanding space inside a simple circle. And here's the trick. As you move from the center out towards the edge, the space itself just expands. It gives you more and more room to work with, exponentially. This is absolutely perfect for language. You can put your most general ideas, like animal, right there at the center. As you move out, you can branch into big categories, like mammal or reptile. And then, as you get closer and closer to the edge, you suddenly have basically infinite room to lay out all the super specific examples. Every single breed of dog, every type of snake, and none of them ever have to crowd each other. And this is the key takeaway, really. This whole thing isn't just about compressing data. Think about it. Trying to shove a big, bushy Christmas tree into a tiny square box is a nightmare. You have to crush it, you break the branches. But if you have a box that's already shaped like a Christmas tree, it just slides right in perfectly. We're not crushing the data, we're just finally putting it in the right container. So how does this actually work in practice? Let's pop the hood and look inside the model that makes this all happen. It's called CGT, and you can think of it as a kind of geometric translator. It really is like an expert packing a suitcase. First, that big, clumsy 768-dimensional vector comes in, then an encoder network intelligently summarizes it, figuring out what's essential and what's not. Then the magic happens. Something called the exponential map folds this summary perfectly into the curved hyperbolic space. And what pops out the other side? A tiny, elegant, super efficient 32-dimensional vector.
And this right here is the mathematical engine that does the folding. Now, you don't need to be a math whiz to get the gist of it. That tan function is basically what squishes everything to fit perfectly inside that circle, that Poincare disk. And the rest of the formula makes sure that the vector's original direction, its relationship to everything else, is perfectly preserved in this new curvy world.
Okay, so the theory is beautiful, right? It's so elegant. But does it actually work? This, my friends, is where the story gets really, really exciting. Let's look at the numbers. Just look at this. The standard model, MPNet, uses 768 dimensions to get a quality score of 0.834. Our new geometric model, CGT32, uses only 32 dimensions. 32! And gets a score of 0.812. That is nearly identical quality from a model that is 24 times smaller. It's astounding. The visual here just says it all, doesn't it? We are looking at a 96% reduction in size, a 24x efficiency gain, for a quality drop of only about 2%. This is not an incremental improvement. This is a total paradigm shift in what we thought was possible. And what this does is unlock a whole universe of new applications. I mean, imagine powerful AI search running entirely offline, right on your phone. Smart devices in your home with zero lag. This democratizes AI. It lets small teams and startups build things that, until now, were only possible for the absolute biggest tech giants. So, let's just pull back for a second and think about what this really means. This is so much more than just a clever algorithm. It's a fundamental shift in philosophy. For decades, we've been trying to solve this problem by throwing more and more raw compute power at it, just brute force. We were compensating for a geometric mismatch with sheer power. But brute force always hits a wall. Alignment, on the other hand, alignment gives you compounding returns. And this quote just wraps it all up so perfectly. The Holy Grail wasn't a bigger, more powerful model. It was a smaller space that was just curved in exactly the right way. The future of AI might not be about building bigger digital brains, but about finding more elegant, perfectly shaped spaces for them to think in. And that leaves you with a pretty big question, doesn't it? What other problems are we trying to solve with brute force that are really just waiting for the right geometry?